is or x simple region, you can start your evaluation immediately. In terms of finding the antiderivative for this function with respect to x, right? So you can immediately start to look for the antiderivative function for this guy, which in this case is not easy. You don't spend too much time in finding antiderivative in all the calculus 3 questions. Because finding the antiderivative is a calculus 2 or calculus 1 question. In calculus 3, I'm not testing you how you can find the antiderivative function for very complicated functions. Okay? I'm testing how you can get around of it. Right? So this one, if x is the variable, not easy. But if y is the variable, it's super easy. Right? So this guy is a constant. You're just taking the antiderivative function for the exponential. So in order to do that, I have to switch it between x simple to y simple. So that's what you do. You always begin your evaluation right after you identify this is whatever type. But you don't spend too much time in finding the antiderivative functions. You with me? If you spend 1 minute or even 30 seconds, you fail to find the easy antiderivative. You give up and switch the other routes. Okay? Never waste your time in calculus 3 question. Be smart about how you deal with the test and the final. So this is a very clear choice. I want to change it to a y simple relation. And then we go for a polar right angle where theta is bounded between alpha and beta, and R is bounded between A and B. Radius bounded between A and B. We also briefly mentioned about R simple region. So R simple region where alpha is less than equal to theta less than equal to beta, R is bounded between two numbers of let's make G1 of theta and G2 of theta. Okay, so R simple region we didn't practice that much, so I don't think I gave you too many questions in here. But R simple region in concept will come up again in spherical coordinate system, which we have discussed. So I want to talk about the R simple region in that regards. But not only that, besides these 5 different types, we also introduced the other two, which is change of variables. So basically, about double integrals, we have 6 different methods to evaluate a given double integral. And these ones are pretty clear. And for polar right angle and R simple region, the clear sign is you see x squared plus y squared in the integrating function, or the domain of the integral is either a disk or some piece of disk, right? So we have the examples where you have only a quarter of disk. Then you have to change your range for theta, okay? So these ones are pretty clear signs for you to choose for a polar coordinate system. Either you see x squared plus y squared in the integrating function, or you see the domain is a disk or a quarter or a half of disk. And the application for all this double integral is to find the area. The area of a region. So a region R, in order to compute the area, we have to take the double integral R of a constant function A. This is going to be the area of R. So instead of giving you a double integral function directly, I may ask you to find the area of a region where I describe the region. For instance, it's a disk with radius 3 or whatever. Then the first step is you have to translate it into a double integral. So the whole midterm is about integration. Every single problem is integration. Some of the questions I might give you the double integral directly. Some of the questions I will give you in terms of finding the area or finding the volume. Right? So these kind of questions. There are some other questions we can also evaluate by double integral or a triple integral. For instance, if I want to find the volume of a solid region D, one formula says I can take a triple integral over D of a constant function 1. right? So this is the way of doing that. Then I can take the triple integral of constant function 1. There are some other cases you don't have to do that. For instance, I want to find the volume of the region bounded by bounded below by z is equal to square root of x squared plus y squared, and above by x squared plus y squared plus z squared is equal to 8. Okay. So this is one of the questions we discussed before. So if I want to use triple integral, I'm simply taking the triple integral of a constant function within the solid region, whatever solid region you have. You can also compute this volume in terms of double integral of an integrating function as the difference between the upper function and the lower function, right? So we have done that before. And we also discovered using the triple integral or using the double integral is actually equivalent, right? As long as you eliminate the z variable, these two are talking about the same thing. And double integral and the triple integral, in terms of finding the area, is very helpful to have a rough picture of it, right? That means you have to at least know what type of these equations, right? So this equation is defining on, what is it? These guys are all surfaces, right? So circle is definitely not the correct word I'm looking for. This is actually a cone, a half cone. Z squared minus x squared minus y squared is equal to 0. So this is a quadratic surface as a half cone. It is half because z is non-negative. Second one is easier. This one is a sphere, right? So this is sphere. So this is a half cone and then a sphere. And this is actually our favorite shape, right? So this is the ice cream shape we have. So lower part is a cone. Upper part is the piece of sphere. So if you want to use triple integral, you have to identify this region in one of the several different types in triple integral regions. And you can indeed identify this as a spherical region. You can identify this as spherical region. Radius is bounded between 0 and whatever is on a sphere, square root of 8. Am I right? Theta is the rotation. You can allow it to go from 0 to 2 pi. And then you need to find the phi region between 0 and this angle. This angle is actually given by 45 degrees. Right? This angle is actually given by 45 degrees because if you restrict it back into the z y plane, this equation has the trace z is equal to plus or minus y. All right? So that's why this angle is given by the slope of the straight line passing through the origin, and that is exactly pi divided by 4. You can identify this in spherical region, but don't be always go back to the spherical region. You can also find the volume of this region by using double integral. All right? The double integral is restricted upon this region. This region is a disk. All right? So this is upon this disk with the difference between the upper function and the lower function. You're simply taking the double integral of the function on the above, which is square root of 8 minus x squared minus y squared. All right? This is coming from the sphere. The lower function is minus square root of x squared plus y squared. And then dA. This is in the double integral. And then I see x squared, I see y squared, I want to use polar. I'll use polar, which means you have to identify this disk in the polar region. What we did before is to find the intersection between these two surfaces, right? You can squeeze it back to the xy plane, but eventually you have to find the intersection between these two in order to find the radius, all right? We did spend quite some effort to do this problem, exactly the same problem, okay? Exactly the same problem. I didn't even change the numbers. Maybe I changed the numbers into simpler ones, okay? So this is a very important application of double integral and triple integral. So if you don't completely understand what I'm saying, go back and review the lecture notes we have. So in triple integrals, we have three independent variables. And we begin from the easiest case, Q, where x, y, z are all bounded by intervals. And that's the easiest case. And then in the easiest case, I'll be able to write this triple integral in 6 different orders. All right? So I give you one order, it's supposed to give me one combination of these intervals. And that's pretty easy. But the harder part comes from the second, third, and the fourth step, which are z simple, y simple, and x simple. Right? So we had actually practiced one very easy question, which this region is bounded by the coordinates plane and a plane. Okay? So if I have a plane restricted in the first octant, and then this region in the first octant bounded by 1, 2, 3, and 4 pieces of straight lines, of planes. This is the region in our tree. I can identify this as z simple region in a space, y simple region in the plane, and then eventually I give you 6 different representations. So you should be able to write down all the ones. Okay, not write down more. For instance, if I ask you one order dz, dx, dy, then you're supposed to come up with the 2 numbers for y, 2 functions for x, and 2 functions of x to y to represent z. All right? And then if I give you one different integrating order, you're supposed to get a corresponding information right here. Okay? So then we move on to cylindrical coordinate system. And the spherical coordinate system. Okay? Cylindrical coordinate system is, I said this multiple times, it's just a polar plus thing. So actually in polar part, you don't have to worry about anything new. It's just the same thing. It's just the same thing as the polar r and theta, which means in triple integral, if you see signs of x squared plus y squared, you want to use cylindrical coordinate system. All right? So if you have x squared plus y squared in your integrating function, you go for a polar coordinate system. It's going to be much easier to evaluate. Okay? Then z is the only variable has nothing to do with polar. Okay? And also in cylindrical coordinate system, I'm supposed to have one extra factor r to come up. Right? So I have one extra factor r. In spherical coordinate system, it's more complicated. And spherical coordinate system is probably the only one. Not probably, it is the only one. Has nothing to do with double integral. Right? All these ones are all double integral deduction. So I have a triple integral, I want to reduce it to a double integral. In a cylindrical coordinate system, when I do that, the double integral is in polar coordinate system. Right? Spherical is the only one you cannot easily reduce it to a double integral anymore. Because if you think about that, there are 3 variables, rho, and theta. Theta is the rotation, rho, phi is the angle you can vary, and rho is the distance. If you have spherical rho, phi, and theta, you don't have easy restriction. You don't have easy connection between x, y, and z, but we can still do that. In spherical coordinate system, the extra factor is rho squared sine phi. You have to remember, rho squared sine phi is the extra factor we have to get out. Okay? We did apply the spherical coordinate system in several different finding volume cases. One of them is very, very nice, which is to find the volume of a ball. Right? If you have a ball with radius r, using spherical coordinate system is very, very easy. Again, you can choose different methods. I'm not against using different methods. Finding the volume of a ball, you can go back using this double integral in order to use polar coordinate system. You can still do that. Okay? But using a spherical coordinate system is going to be the easiest. And this is not all of them. We can still evaluate triple integral in exchange of variables. In change of variables, I didn't give you any examples in class, so eventually I'm not going to test you in change of variables in triple integral for the following reason. Remember, when we do the double integrals, we have the boundary defining functions, and we introduce new pair of variables for the reason to simplify the boundary defining functions, all right? So if you have a region in R3, the boundary defining functions is going to be much more complicated, am I right? The boundary defining functions, if you have a cube or any hexagon or whatever polygon shaped things, the boundary defining functions are going to be functions involving 3 variables, and then you have to choose a triple of new variables to simplify that functions. It's not going to be easy. So in the online homework questions, they already gave you the formula of new variables. Then you need to compute the Jacobian. It's much easier, right? So if I give the region, then you got to decide which new variables you're going to introduce. That's more difficult. So on the online questions, I only need you to be able to compute. Listen carefully. I only need you to be able to compute the Jacobian if you already have the formula for the new variables. Okay, so I don't require you to come up with the formula for the new variable. Okay, so that's the thing I'm requiring. So in spherical coordinate system, I think I have probably one more. Not really. I didn't design too many complicated questions. So in any case, the questions I gave you are all simple numbers. Okay, so you don't have to use calculator or anything. I'm supposed to begin our introduction of new chapters, but I guess you guys are not in the mood, are you? No. So according to the calendar, I'm supposed to cover chapter section 14.1, 15.1, which is about vector fields. So I will talk about this in next Monday, but I want you to spend some time to read this chapter section. This is a super easy section, okay, very easy section. And online home questions, I check about that. Only 10 simple questions you need to compute what the vector fields are. So good luck on Wednesday.